Good evening, and thank you all for joining us here tonight in the beautiful Elm Theater, and I am delighted you're here. I am Barbara Karamedjev, co-founder and board director and president of the American Computer and Robotics Museum. And it's my sincerest privilege to welcome you to the 22nd Stibitz-Wilson Award.
So what I was hoping to do over the next several minutes is, give you a chance to share a bit about your experience, your expertise, especially in this important field. And so first, you're best known for your work in surgical robots. Can you tell us a bit about how you came to work in this area and how it fits into your earlier work?
Okay, sure. After I did my PhD, actually at the Stanford Artificial Intelligence Lab, with a focus on how you can use sensing with robots to develop programs that would robustly assemble things, I joined IBM Research, where I actually was there for 19 years, and for the first part of those, research was primarily focused using manufacturing problems as drivers. But a lot of it involved really a partnership already between people, manufacturing engineers, and line personnel, technology, and information to improve manufacturing processes, a lot of which involved already sort of a human-machine partnership. But I wanted to spend some more time doing one or two really highly focused technical things. And so I basically took an internal sabbatical. I took about a year, hired two postdocs. One worked on with me on this hip replacement surgery project, and the other was we worked on basically a surgical navigation project. And the result of that was we actually developed a prototype that could do surgery on dogs. We were working with Hap Paul and Bill Barger at UC Davis. And then they built a system that became known as RoboDoc for preparing the bones for hip and knee replacement surgery. Well, again, there was this three-way partnership between surgeons, technology, the robots, the vision systems, the sensors, and information to do better treatment processes. And already at that time, I realized as well that you had the potential, because you knew much more about what you did if you knew the outcomes, you could do what we now call deep learning. At that time, I called it process learning, to improve the process for the next patient. And so I built a research group in IBM. And we did a number of things in surgical navigation and also in robots, both with hand-over-hand robots and robots for minimally invasive surgery, for laparoscopic surgery. And there was a system for that we called the LARS, which we actually had a lot of intellectual property on. And we developed a surgical navigation system for craniofacial osteotomies, where that was basically donated to Court Cutting at NYU Medical Center. But I realized that if you really wanted to do that, what you really needed to do was be in the same institution as the users, as the surgeons, so you could work with them without a lawyer in the room. And we were developing this laparoscopic surgery robot with in partnership with Johns Hopkins, and I eventually just decided it made a lot more sense to move to Hopkins, where there was great engineering school and a superb medical institution that worked together and were in the same institution. So I came here in 1995 and wrote a very large proposal to the National Science Foundation, where we got one of these engineering research centers for computer integrated surgical systems and technology. And that really was the basis of the main focus of my research since then, both while we had the NSF grant and afterwards. But again, everything really revolves around this notion of people, technology, and information to improve processes, both for the individual patient and for improving the whole system.
So building on that a little bit, and you mentioned the NSF ERC, you refer to computer integrated surgery, and I'm guessing it has much to do with that partnership idea, but can you say more about what that means?
Sure. What you're interested in is the use of technology and computation really to exploit the mutual benefits or the complementary abilities of people and machines. And if you think about it, there's still no equal to these. But if you're getting inside the body, there are places where our hands are too big. And also, often our ability to deal with things like hand tremor or very precise motions, or to relate, say, a image onto a target, are things where a robot has much higher precision and can do things like enforce safety barriers. The robot isn't the surgeon, the robot's a tool. And what we're really trying to do is create an environment where surgery can be safer, more effective. You can do things you can't do at all. And it's not even just surgery, it's interventional medicine, injections, local therapies. So computer integrated surgery seemed a much better word than robotic surgery because it's more inclusive.
Sure. So that's interesting as well, because I mean, you've mentioned your background when you were at Stanford in AI. AI comes into a lot of what you do. These days, there seems to be a lot of impression, especially in robotics, of AI leading to autonomous systems. Yet that's not what you're describing here. So what is the role of autonomy in terms of where we're going?
Okay, well, it depends on what you mean by autonomy.
Fair.
Controlled robots, the computer is already doing a lot.
Right.
And you see these analogies that were popular when people talk about self-driving cars, and the DoD has, and you talk about level 1 or level 0 autonomy, which is basically you're throwing a rock, up to level 5, where I guess for surgery you would be wheel the patient in and take out my appendix. But I always think it is, in a way, constraining and both over general and over specific. You get yourself into these philosophical discussions. Is this level 3.2 or 4.1? And if you think about it, any of this really relates to two key questions. The first is, how can the machine be told what the machine is supposed to do? And the second, and whether that is some motion or whether it is providing information. And the second question is, how can the machine have the information and be trusted to do what it has been told to do and not to do something that you really don't want it to do. Now, if you think about it, we've put a computer between the surgeon and the surgeon's tools, and you can begin to take more advantage of that. Also, we've put a computer through, say, stereo TV between what you're seeing, especially in things like endoscopic surgery, and the surgeon's eyes. So you can begin to take advantage of that to augment the surgeon's ability, information, and also to provide more levels of control up to, there's some things, well, even with RoboDoc, that system, the planning was done offline. We called it surgical CAD/CAM. You made a plan based on medical images of, here is where I want this implant to go. The surgeon then did some sort of hand-over-hand guiding to set the system up, which would then do something to do registration, to relate the physical patient to sort of the virtual patient of the CT image in the plan. And then while the surgeon monitored things, the robot would cut a shape in the bone. You can also think about cases like needle placement. Now that is often done interactively, but you still have some kind of either a preoperative plan, or in the operating room or interventional suite, you have an image, surgeon kind of designates a target, and the robot can go over and either do the whole injection or biopsy or whatever, or it can just give information to the surgeon, or it can do something in between. Now, there's one other point, and I'm sorry if I'm rattling on too long, that comes back to this autonomy. For this partnership to work, whatever the role of the two partners in the team are, you really need a shared understanding of what the task is and what the environment is.
Mhm.
So if I think the surgical CAD/CAM model with RoboDoc, what we did is we planned everything preoperatively, and then we would just run a simulation based on the motion of the robot, so the surgeon would know what's going on. But what we'd really like to do is have that digital twin model, and I personally don't much like the term, but that's what everyone uses these days. It's become the latest buzzword. You'd like to do this information fusion so the system is aware of everything in ways that are interpretable by the surgeon and by the I'll say the robot, by the system. And so that's where we're really headed, and we've made some pretty good progress on using this head and neck example.
What thoughts do you have in terms of applications outside of surgical robotics for the type of work you're doing?
Okay, sure. And again, within surgical robotics, there are a couple other things I see as really important in the future. I do see these systems becoming smarter and smarter and more effective partners to surgeons and caregivers. We had smart factories when I was at IBM. What we have, and we're pushing on here, are ambient intelligence in care rooms. In operating rooms, you would like the room itself to know have all the information about what is relevant to what's going on in the room available, and can be used for machine learning. It can be used to help control the machines. It could be used for things like near-miss warning. I've been interested and now see more and more opportunities in ICUs and other care rooms in the hospital to do a variety of tasks. especially if you can have now an affordable mobile robot with a couple arms and vision capabilities. It can do some tasks. It can, if when we have our next pandemic, it can go into contaminated rooms and be much more versatile than this thing that just clamped onto the ventilator. I'm also getting more and more interested again in using manufacturing problems for, again, coming back to this three-way partnering idea, but also just automation.
Well, and again, thank you, congratulations for receiving a 2024 Stibitz-Wilson Award,
Thank you so much.
recognizing your work in medical robotics and computer integrated surgery.
I really am very, very honored. I've gotten various awards over time, but this one also means a lot to me, and I really am grateful that people thought of me, and I do wish the best to the people who will be attending the event. And again, I really wish I could be there. Some of it is the fishing, but primarily it's to meet with people there.
Of course, of course.
Okay.
Yeah. Well, thank you again, Russ.
It's a real honor to be here. This is my first time in the state of Montana, and I really appreciate the hospitality. I just want to try to share with you for a few minutes kind of the obsession that's really driven my life, and that's a life of sound. For some reason that I've never been able to quite understand, music has been almost all I cared about, other than people. And it's really formed the basis and motivated almost every decision I've made in my life. I didn't have the courage to be an artist. I say that in the most honest way that I can. I'm a musician. I'm not bad, but I'm certainly not great. And knowing that about myself led me very clearly to feel that I should never become an artist. But I revered art so much that I wanted it to be the centerpiece of my medical career. And so as a surgeon, I've pretty much now focused everything I can on the ability of people to hear music, and then also trying to understand the mechanisms by which we generate this elusive thing called music that I love so much. And so I'm going to take you on a whirlwind tour of what I've done, and hopefully give you a little bit of insight into why these questions are so intriguing to me. Can I go to the next slide? Is there a clicker somewhere? Okay, great. So when everybody thinks of different things when they think of music, well, this is what I think of. Right? And so this is the temporal bone. And so for those of you that have never thought about how it's possible for you to hear, just take a moment to reflect on this structure. Sound is a vibration in the air that goes through the ear canal and sets our eardrums into motion. That motion of the eardrum then transmits vibrations down 3 small bones that then enter the inner ear, where an amazing thing happens, where acoustic energy becomes electrical. Beyond the cochlea, which is the inner ear, there's no more acoustics. So you don't have acoustics in your brain, okay? You have electricity in your brain. So with that idea in mind, that the purpose of the auditory system is to take these acoustic vibrations, to recreate them as an electrical percept in your brain. Let's listen to some music together. And if we could click the next slide. It's easy to take for granted what just happened, but it's absolutely not possible for me as a hearing restoration specialist to take that for granted. We have heard the auditory musical vision of a genius composer who himself had hearing loss now, many, many years later, by electrical recombination of acoustics in our brain. And it's a remarkable thing. And that was what I wanted to understand when I entered the field of otolaryngology. And I thought to myself, okay, I'm finally going to get to understand music. But when I got there, I heard a lot of this. Next slide. Blips and beeps. And so unfortunately, my field, when I entered it, was really a field about blips and beeps. And the more I was thinking about blips and beeps, I just kind of felt that I was getting further and further away from music. And so next slide, I'm going to introduce you to a girl. This is Grace. Let's go ahead and advance to the next slide. This is Grace with her mother.
Yeah. Ow. Ow. Yeah. Baby. Baby. You want it?
Beautiful child, beautiful family. And for those of you that may have some experience with this, you may notice one thing. This child is profoundly deaf. Okay? So she doesn't hear anything that her mother is saying, and her mother's doing everything she can to deliver sensory input to this child. Now, in the past, next slide, please, we didn't have a lot of options when somebody was born deaf. And we actually had funnels and ear-shaped objects that we would stick in the ears. And today we have the modern multi-channel cochlear implant. And if we could have the next slide. And this is my team performing a cochlear implant surgery. I began my career at Johns Hopkins, and I'm currently at UCSF. And cochlear implantation has been the kind of centerpiece of my surgical career. So this child's family made the decision to pursue a cochlear implant. And it's a personal decision. It's not the right one for everybody, but that's what they wanted to do. And so now I'm going to show you a video of this same girl. She was implanted at around 1 year of age, and here she is 11 years later talking to us. If we have the next slide, please. And then advance to the next.
So you've written 2 books.
I've written 2 books.
Was the other one a book or like a journal entry?
No, the other one was a book.
Oh, okay.
But, yeah.
Well, this book has 7 chapters, and the last chapter is entitled "The Good Things About Being Deaf." Do you remember writing that chapter?
Yes, I do. I remember writing every chapter.
Yeah.
Well, sometimes my sister can be kind of annoying, and so it comes in handy to not be annoyed by her.
I see. And who is that?
Collie,
Oh, okay.
Her sister.
Her sister.
my sister.
And how can you avoid being annoyed by her?
I just take off my CI and I don't hear anything. So it's pretty, it comes in handy.
So you don't want to hear everything that's out there.
No.
So this girl is incredible, and what you're really seeing is a true miracle of modern medicine. That we can now take somebody who's deaf and restore their hearing to a really remarkable degree. And we're furthest along in auditory restoration of all the senses. If you were to lose a sense today, the one that we could do the most about medically or surgically is in hearing. Now, even though she's great at speech, a funny thing happens when she turns on the radio. And so rather than hearing a piano that looks kind of like this, can I have the next slide, please? It looks and sounds a lot more like this to her. Okay? And so why is that? These devices were never meant to handle music. In fact, they're just not powerful enough. They're not good enough to handle music. And so what happens to a musical signal is it gets highly degraded. In fact, many, many errors, many things that you would think of as counterintuitive, keys that are missing or absent, keys that are particularly wide, the melody going down when you should be going up. There's a lot of reasons why it fails. And so a lot of my work has been centered around this idea of how do we take a cochlear implant user who's been deaf and give them music back? How do we give somebody the gift of melody? And if we can have the next slide, please. It's not an easy thing to solve. And the real reasons why is because language, it turns out, is a much simpler acoustic signal than music. Music can be almost any sound. And so if you look at the dynamic range of music, if you look at the frequency spectrum of music, it far exceeds that of speech. And also it's abstract. And there's this issue with music that if it doesn't sound good, what's the point? Whereas with language, you mostly want to know the information. Yes, I'm sure you hope that the tone of my voice is pleasing, but mostly you want to know what somebody is saying. And this is why a telephone works for speaking to somebody, even though it doesn't sound that great. And if we could have the next slide. And so this is a schema showing you all the things that cochlear implant users cannot hear well in red. And you'll see right away that the pitch is in dark red there. So cochlear implants are entirely out of tune. And so right now, it can be out of tune as much as 1 octave. And so for those of you that are musicians, like imagine the first thing you do is tune your instrument, but you tune it out by an octave. And it's not a linear transposition of an octave, it's random detuning. And so you can see right away how music doesn't stay what you want it to be. And so hopefully one day we'll be able to tell you, and I always hope my best work is ahead of me, hopefully one day we can tell you that we've solved this issue and that now if you lose your hearing, you can get it back perfectly. Right now we're not there with perfect hearing restoration. And so that's just a little summary of kind of the motivations I have for wanting to use music as a tool to understand hearing restoration. If I can have the next slide. Now, I mentioned that I'm sort of a struggling musician, and I'm a saxophonist by training, and so I have spent most of my life trying to understand how to improvise on saxophone. And I knew very intuitively that when one starts improvising, being creative in musical terms, something changes in the brain. It's not the same idea as when you are doing something didactic, not the same as doing something memorized. And I wanted to get to this root of what happens in a jazz musician's brain. Can we play the video now? So this is a plastic MIDI piano keyboard that we use for the jazz experiments, and it's a 35-key keyboard that is designed to fit both inside the scanner, be magnetically safe, have minimal interference that would contribute to any artifact, and have this cushion so that it can rest on the player's legs while they're lying down in the scanner, playing on their back. And it works like this. This doesn't actually produce any sound. It sends out what's called a MIDI signal, or a musical instrument digital interface, through these wires into the box of the computer, which then trigger high-quality piano samples like this. And now I'm going to demo this for you. And this is going to be memorized music. Improvised. That dumb piano took me 2 years to make. It never worked, and then one day it worked. And so at this point, I was at the National Institutes of Health, essentially in the basement, left alone, so nobody knew what I was working on. And so I was like bringing in jazz musicians to the NIH and saying, come on, let's play some blues. And so I had them play the blues, and this is a summary of what happens when a professional jazz musician starts playing the blues. When you improvise, you turn off huge portions of your lateral prefrontal cortex. These are conscious self-monitoring areas of your brain. And so right now, this part of my brain should be quite active because I want to make sure I don't say something too stupid. I'm monitoring myself pretty carefully. But in jazz, it's actually the opposite of what you want to do. In fact, in creativity, it's very likely the opposite of what you want to do. You don't want to choke off the inspiration for creativity. You want to take risks. You want to not worry about being right or wrong. You don't have to think about correct. You want to get in some sort of flow state or some sort of zone where you can let the brain do its thing and generate creative ideas. And so we think that this is one of the hallmarks of high-level expert creativity, is this ability to shut off portions of the prefrontal cortex. And this spawned a whole line of research, which I won't get into right now, but suffice to say that we're asking now questions that used to be off limits. You know, art used to be over here and science over here, but now science is being used to investigate why the arts have always been so significant for humankind. Next slide. And we've had a number of colleagues along the way. These are just some of the musicians that have participated in these experiments and in this movement for us. And we've really been blessed to see that musicians have as big of an interest in the neuroscience of music as the neuroscientists. And it's led to this thing, next slide please, where we've asked the question of, one more advance please, of music as medicine. And so is it possible for music to be used therapeutically? And through a long series of conversations and symposiums and lectures, basically the National Institutes of Health has been convinced now that music should be something that they should target as an area of research. Next slide, please. And this is two very important people. One is Francis Collins, the former director of the National Institutes of Health, and the other is esteemed soprano Renee Fleming. And the three of us got together here at the Kennedy Center to discuss the merits of funding scientists that want to look at music, make music an actual valid topic for study. And if we could have the next slide. And finally, they agreed to fund $20 million to support music research that's now been $40 million and hopefully will continue to be additional millions of dollars. It's not a lot compared to a lot of diseases, but it's certainly a lot compared to what the arts have traditionally gotten out of science organizations. And so with that in mind, we're kind of moving ahead to try to bring this into common awareness. We want everyone in the world to understand that music is not just entertainment. It's more than that. It's a way to improve our lives. It's a way to heal us. It's a way to make people feel better about existing. And it's also a way to treat various neuropsychological conditions that are out there, and ultimately to connect humans to one another. And so I just want to thank a bunch of people. None of this work was really done just by me alone at all. And so I want to thank institutions and funding sources that I've been a part of. Next slide, please. These are various members of my lab over the years. Nothing would have been done without this group of people. Next slide, please. These are scientists that I've had the good privilege to work with, and I really owe everything to my mentors. And then finally, one last slide. And these are artists and musicians that I've had the great privilege to collaborate with over the years, and I really, really am indebted to them for their participation and their collegiality. And with that, I'd like to just thank you for your time this evening. I'm truly honored with this award, and I thank you so much. I guess I'm not leaving.
Would you be willing to answer a question or two?
Absolutely.
Very quick, thanks for your presentation. So you've been able to blend your work in scientific studies with these work with artists and musicians and so forth, and what do you see as the prospects for that work continuing? Has the success led to future ideas for funding and more work?
I think we're truly just scratching the surface. So this is a field that's very nascent. I think the power of arts speaks for itself in the fact that it's existed throughout human history. You know, why? Why have there always been the arts? Humans are hardwired to create, they're hardwired to perceive music. It matters to being alive, and I think it's because it allows us to communicate in a way that's beyond the limitations of language. It's a very good way to connect people together emotionally. And so when you think about how fractured our world is today, how much depression there is, how much psychological loneliness there is, I think the power of music is untapped. And so I truly hope that it's the beginning of a movement. And I think the NIH is catching on, and I hope our science can live up to the challenge.
That's wonderful. I share your optimism about that. You mentioned that cochlear implants have been remarkably successful in returning speech recognition to listeners, and it's such a delight to have that. What have you learned, or are there things that you think can be applied to other types of sensory brain interfaces like the retina and other areas? Are there lessons that we can learn from the work that you've accomplished?
Yeah, thank you for the question. There's absolutely lessons to learn. Now, you might have noticed that the cochlea has a very particular geometry to it. It looks snail-shaped. That snail shape is actually critical to the success of the cochlear implant because the geometry is relevant. There's a spatial gradient of pitch or frequency along that snail shape, and that means that if you insert an electrode into the snail-shaped structure and assign the pitches at the correct location, you get fairly close to what it should be. Unfortunately, the eye, for example, doesn't have any such mathematical organization, or it does and we're not yet able to identify it. And so the question is, how do you identify what the rules are in the neurons that you're stimulating? In the ear, the rules are somewhat apparent to us, but it's not always the case for other things. And then when you get to things like olfaction or smell, where it seems like there's almost a random combination of things that can trigger smell, you can see that the problem is immense. But I will tell you, the success for a peripheral stimulation of sound compared to putting an electrode on the brain or putting an electrode on the brain stem, we're much more successful in the periphery. And so I think it's a clue about what we need to do to improve, in a way, restoring the defective organ back to its original state of function, and then letting the brain do what it can with the intact signals.
Wonderful. Thank you very much. Let's please congratulate Dr. Lim one more time for his award.
Thank you so much.
So, I'm from Great Falls, Montana. I was born in 1939. Going to school in Great Falls was actually terrific because we had good teachers and we had no social hierarchy. that would put you in your place. You were what you were, and you were regarded for what you did. A very lucky thing happened to me that a German doctor, Ernst Eichwald, whose father was Jewish, was in Freiburg at the beginnings of World War II. And one of his group of colleagues left Germany when he was arrested by the SS. And they all knew that they had to get out. He got out. He went on the faculty at Harvard. He was pretty good. Then Utah. And then he answered an ad to come be the hospital pathologist in Great Falls at the Montana Deaconess Hospital. And he was just sort of thinking about it until he drove through Wolf Creek Canyon. So that's between Helena and Great Falls, and it really is beautiful. And he leaned over to his wife and said, "I'll take any offer." And so there was, for me, somebody who was doing biomedical research. One of my good teachers, when I was 10, gave me a copy of a book called Microbe Hunters. And this was just a little bit fictionalized account of the great beginners of looking for microbes as organisms that can cause disease. Paul de Kroof was the author of it. And the little bit of fiction that was there made it human. And the amazing thing to me was not only the discovery and how when you get close to making a discovery, you're very intense. There's very little else you can focus on. But then each one of them in that book, turned to see what could this discovery do if it was translated into something in preventive or actual therapeutic medicine. So I remembered all of that even though I was 10 at the time, and subsequent years in high school proved that I wasn't really good at remembering things that would have counted for grades. Never got close to that. But I began work with Ernst Eichwald, and luckily he had made a big discovery about when you do skin transplants from one individual to another, he used mice, that if they're not genetically related to each other, they reject the skin graft in maybe 10 days to 20 days, and was working out how you could define the genetics of the rejection, and that led into the immune response. And he was good enough that scientists would come to visit, and here I was, a high school student, not knowing that I should revere the scientists who were coming to visit Great Falls, Montana, because, like the last award winner, they always had fishing on their mind. It was Great Falls was fun, but where do I go fishing? Now, in 1945, two things happened, both of which were necessary to develop the field I actually went into. Of course, civilian populations in Hiroshima and Nagasaki were exposed to very high doses of radiation. The highest dose that killed below the blast killed by wiping out somehow the nervous system. A lower dose killed by wiping out the ability to have an intestinal tract that was going to keep the water of the body from going out of the body. Nothing you could do for either of those. At the lowest dose, though, that killed, they lost the ability to clot their blood and to fight off infections. And that was something that interested a number of people. The year that I began working with Ernst Eichwald, there was a wonderful paper coming from England. Well, let me go back. I forgot one person in this story. the person who actually visited. In 1945, Ray Owen, a graduate student at the University of Wisconsin, was doing genetic experiments of blood transfusion in cattle rather than humans. And he got twins that were fraternal twins, male, female, and he found that a number of them, the female, didn't develop female secondary sexual characteristics, breasts that would enlarge, uterine that would hold a baby, and so on. But he found also, when he tried to test their blood, that instead of having the genetically defined blood groups that we get tested every day for us, and they get tested for theirs, the twins had each other's blood. So it wasn't just each other's blood, they had their blood, and they had each other's blood, and there was no way you could explain it genetically. And instead of him backing away from it, he says, must be something that happened when they were together in the uterus. And it turned out they shared a placenta. And by sharing a placenta, the blood from one would go to the other. It would carry a substance from the male that would prevent the female from having a development of the secondary sexual characteristics. And it would carry blood cells. But we didn't know how blood was made. He also knew that if they hadn't been twins, those two, and they were just the kind of genetics that would be individually, that if he transfused the blood from one to another after they were born, they would make an immune response, antibodies, and it would be a transfusion reaction that didn't work. But these persisted. So by his observations, he predicted, well, there must be cells that form the blood. They must be shared between these two. And there's something funny about the immune system, that it takes stock of what self is. And anything that's self, it's got to eliminate the immune response against it before you're born. But anything that's not self, like an infectious microbe that could occur during development, fetal development, you would be able to make a precise immune response. So it was that set of discoveries that started the field going, and Eichwald was working on transplantation. And then the group in London, led by Peter Medawar, and he had two people working with him, said, well, if it works in cattle, why don't we just do the same thing and take the blood-forming tissue, bone marrow and spleen, and inject it into a fetal mouse where we have it from a different donor. And amazingly, they could see the blood type of the donor and the recipient. And they did skin grafts between them, and the grafts were accepted, not rejected. So now this was essentially proving the hypotheses of Ray Owen. So as things happen sometimes, Sir Francis Burnett, who predicted the immunology part of it, got a Nobel Prize. Peter Medawar, who repeated Ray Owen's experiment, got a Nobel Prize. And Ray Owen got a letter from Peter Medawar saying, that was great, thank you. So Ray Owen visited us. And I was completely fascinated with his story. And I thought, gee, if the blood-forming system can reproduce itself and can be transferred from one to the other, maybe I could go after how that develops the immune system that takes account of self versus not self. And one way or another, I wish I could say it was direct, that I knew it was going to happen. Charles, you did it the right way. I did it the other way. And that is, do experiments and then observe what you see. And to make a long story short, I did research continually from high school to college and into medical school. In fact, in the first 2 summers after medical school, I still came back to Great Falls to do research there. But I was lucky also that at Stanford, we had a special program that medical school would take 5 years instead of 4. And that was so that the medical students could have a half-day free every day when they were taking classes. So they had to spread the classes out to 3 years instead of 2, 3 years of basic science, 2 years of clinical. And you had a half day every day to do research or other scholarly work. Stanford had a lot of opportunities. And the time that you could do that made you go out and interact with the scientists you wanted to work with. I was very lucky to have a patron, Henry Kaplan, who developed the linear accelerator for cancer therapies. A guy who made a discovery and immediately translated it. So, somewhere in the late 60s and early 70s, a husband and wife couple, Len and Lee Herzenberg, developed what they called a cell sorter at the Los Alamos facility that led to the development of the atom bomb. There were people looking at how you could use droplet generation, maybe for printing or for something else. And they caught on that maybe you could stick cells in each droplet. And then if you could put a charge on the droplet according to what the information was in the cell, run it through a magnetic field, then it could be collected in 2 different test tubes. So I tested that, and we made antibodies, looked for those that might be involved in only half or a third of the bone marrow. And here's the next great scientific advance. I did remember that whenever we went on road trips, my family played 20 questions. Raise your hands if you played 20 questions. You know what I'm talking about. Okay, good. So, you know, if you got a yes or a no, let's say you get a yes, then you move on to the next question. If that first yes got rid of half of what was there but kept the other half, then you could divide that in half, the second and the third, and 2 to the 20th. That's what you're really doing, is 1 million. You could find anything that had only a frequency of 1 in 1,000,000. And with that, in 1988, we found the blood-forming stem cell, first in mice. We had to develop some mice that were humanized to the point that they could accept a human blood-forming transplant eventually. And it was the early time of AIDS, so I had a spectacular fellow, Mike McCune, and we humanized mice, and we said, we're going to do 2 things here. We're going to try to find the human blood-forming stem cell, and at the time, we're going to see if HIV will infect these mice, the human component of the mice. The epidemic was raging. There were scientists who said it wasn't a virus, it was their behavior. You know, you hear all of that kind of thing. And the mice got infected with HIV, and it caused AIDS in the mice. So I went to my department chair, who was then the dean, my former department chair. I said, we need to get a safe place to do these experiments. We need more space. And every academic will know what I'm going to say. They say, well, gee, if you've got the money and you know a place you can put it, and so on and so on. Because they were concerned with more important things like how much money isn't lost this year, and who can we recruit, and so on. So we had to form a company. And we did. It was called Systemics. And within 2 years, we got the human blood-forming stem cell. My wife was one of the senior authors and led the group that isolated the human blood-forming stem cell. And we moved into clinical trials almost immediately. So now we had the cells that can make blood. We had isolated them down to pure cells with that cell sorting technique. We found that they were only 1 in 100,000 cells in the bone marrow, so it was worse than a needle in a haystack. We found we could transplant them into those mice that had human components, and they would regenerate the blood-forming system. We, of course, wouldn't have the same individual as the donor and the individual whose tissues were used in the mouse to form the organs of a blood-forming system. So we were back at the problem that my first mentor, Ernst Eichwald, was dealing with. Can you overcome the rejection? I'll just say we did. And then we went into clinical trials for women who had metastatic breast cancer. So it was beyond the breast, beyond the lymph node. It was in the lung or quite often in the bones. And once you have spread cancer, no local therapy like radiation or surgery can cure the disease, because there will be cancer cells out there and they will come back. So we decided to use the combinations of chemicals that people were using to palliate the disease. Except we moved to 10 to 100 times that dose. And of course, we expected that they would die of blood failure, because while we're trying to get rid of the last cancer cell in the body, we also got rid of the last blood-forming cell in the body. So we had to rescue them, and at the time there was a fad that people would take the whole bone marrow from the woman, give her the high-dose chemotherapy, follow that with the bone marrow back into her body to rescue her. And that seemed good, except I mentioned to you that most often site of metastasis is the bone and bone marrow. And we eventually figured out that as the cancer spreads, the breast cancer spreads, quite often it's in the bone marrow. Quite often, when you reinfused it, you reinfused the cancer. But now we had that as the standard of care, and we put back their blood-forming stem cells purified. And the purification itself deleted all the cancer cells, 250,000 full depleted. We also, at that time, were thinking about what else can we do with blood-forming stem cells. Oh, good. I thought he was going to take that hook. All right, I'm still going. Yeah, just a minute. Okay. Many people are born with genetic diseases of the blood formation. Sickle cell anemia, Mediterranean anemia, juvenile diabetes, lupus. You can have not enough cells or the wrong kind of cells. And from even that early time, people thought, well, can we, with genetic modification, as Jennifer Doudna does, another Stibitz Award person, But that means you've got to get out the right cell, you've got a precise edit, and then you're going to put it back in. And it was tough. And we said, being kind of crude and stupid, why don't we just take stem cells from somebody who doesn't have the disease and is closely related enough that we don't have to give them powerful immune suppression. And I'll just say it worked, and we got rid of all of the side effects of transferring all the blood cells, including the ones that could make an immune response of the donor against the host when they came in. That's why people are hospitalized. That's why people die early after that kind of a treatment. And if you do just stem cells, that doesn't happen. So now suddenly we're thinking about, we could treat people with cancer to a higher dose and see which ones we could improve their life. And a very large pharma said, you don't have enough money to do those clinical trials, but we promise we'll do the trials. And so they bought our little company. We had formed a company, now it was bought. Well, I waited around as we were seeing this terrific result come through for the women with breast cancer. And they never announced a trial. They didn't call us up for advice. They just, about 6 years after they bought us, just shut it down. And I learned one of the biggest lessons of my life, late in life, of course. That is that, and I'm not going to say it in a derogatory way, so don't take it that way, but the only function of a company is to make a profit. And if you're a company and you don't make as much money as you can, as fast as you can, by your own judgment, the SEC will honor the shareholder suits, and you won't be a company anymore. So that's a hard one. So I finally got to understand why they wouldn't do it. In the meanwhile, my wife and I started a company, and she led the search for brain-forming stem cells, did many clinical trials. If we'd had blood-forming stem cells and brain-forming stem cells from the same person or the same embryonic stem cell line, we could just change a number of diseases, spinal cord injury, age-related macular degeneration, and so on and so on. So I'd like to make this like the Hollywood ending, and we have it all, and we're going forward. But the main point is that we got where we were through observation. We got where we were because I grew up in a classless town called Great Falls, Montana, and didn't respect the opinions of those who were, they said, smarter or better, or more understanding of the financial aspects of it. And Ann and I have retrieved all of the intellectual property and all of the cells, and we've validated them. So, like Charles, I'll just say, we aren't done yet. I said, I ain't done yet in an article so they can know where I came from. And we're going forward. Now, usually, for those who could count, I was born in 1939. Usually at 65, you're kicked out of your job in a university. But I wasn't kicked out. And right now, I am in my job still. I stepped back from administrative responsibilities. And yesterday, was it yesterday or this morning, I found out from Charles, the previous speaker, that the dean that is ignoring my age was one of his mentors at Johns Hopkins, Lloyd Minor. So I'll finish this now by saying I totally appreciate the opportunity I had to grow up in Montana, I appreciate that I was able to follow my own nose and do my own experiments on observation. Nobody got in the way. Nobody told me what to do. And that my time at Montana State, I had better science, philosophy, history, and chemistry teachers than I ever had at my previous college, which I would tell you the name, but I don't want to have a lawsuit. So I'm very, very grateful to the Stibitz-Wilson Foundation. And my last little point I'll make is that I was in Bozeman for an award, it must be about 10 years ago, and I sat down with Waded Cruzado, and she said, "So tell me about Renee." I said, "Renee who?" She said, "Well, Renee Ray-Opera. I'm going to hire her as my vice president for research." So I got over that after a while, and Renee and I have been great friends, so that when the institute that started with Ernst Eichwald, the McLaughlin Research Institute it's called, for a while at least, when the opportunity came up that Renee was available, I was able to help the town of Great Falls, the trustees of the McLaughlin, to recruit her, and it has been wildfire since then. I knew she had it, and it's absolutely terrific to see that many, many more students in Great Falls who will get their high school training at Great Falls High School, and I heard there's another high school now, and then come to Bozeman for their education. Thank you very much.
We got a plaque for you. Thank you so much. Thank you. Thank you, Dr. Entenmann, for the kind introduction. I am incredibly honored to receive the Stibitz-Wilson Award from the American Computer and Robotics Museum today. Growing up as the daughter of Indian immigrants in Eastern North Carolina, I never would have imagined sharing this stage with such trailblazing innovators. So I'm going to tell you just a little bit of the story of sort of my zigzag life and where I've ended up today. Science has always been a part of my life. Growing up, I was an avid reader of science news, watched Nova, and tinkered a lot, which opened me to a world of possibilities. But what really got me hooked on science were the great teachers and mentors in my life. I went to an under-resourced elementary school, but I had fabulous teachers. In 6th grade, Mr. Wilkerson made science really fun. One day, Mr. Wilkerson brought to class an old wooden chicken incubator and some chicken eggs. And over the next 21 days, I opened an egg carefully every 2 days and wrote down my observations about the embryo's growth. I remember the awe I had of witnessing a chicken embryo develop over a period of time. Mr. Wilkerson made science really cool. Moving to 8th grade, I was able to work with a great mentor, Dr. Prem Sahgal, a botanist whose lab I had the opportunity to work in and study the growth of duckweed. Duckweed is a potential source of food because of its high protein content. It doubles its growth nearly every day. It was an amazing plant to study, and my mentor, Dr. Sahgal, taught me the skills required for rigorous scientific research. I also entered my research project in local science fairs. Eventually, I was fortunate to enough to attend the North Carolina School of Science and Mathematics, the first public residential high school for juniors and seniors who wanted to follow their passions in science, technology, engineering, and math. It was at NCSSM, through their mentorship program, that I worked in the microbiology lab of Dr. Vickers-Burdett at Duke University. She gave me the opportunity to conduct research and later compete in the Science Talent Search. In my time, it was called the Westinghouse Science Talent Search. I still remember the title of my project, Isolation and Characterization of a Tetracycline-Resistant Plasmid of an Animal Isolate Streptococcus faecalis SF2. Still remember it. With all these experiences under my belt, I went off to Bryn Mawr College to study biology, and I was on the path to obtain an MD PhD. But college is all about finding yourself and what really gets you up in the morning. What makes you passionate? At Bryn Mawr, I had a wonderful professor told me, if you want to understand people's motivations and aspirations, get a backpack and start traveling for a year. You only get it once, kid. Do it. The year after I graduated, I was given the opportunity to do just that. And it was then that my career path took an unexpected turn. On a Rotary International Fellowship, I had the chance to travel from Thailand to Pakistan for a year. And one day, when I was in the eastern part of India, I got off a train and saw a group of kids sitting in a circle on a train platform, learning how to read and write. There were 50 kids, and there was a teacher in the middle teaching them with flashcards. And I learned that these children live on and around the train platform. They work, they play, they bake, they sleep, they eat, but they don't go to school. So a social entrepreneur brought the school to the train platform. Two questions struck me then. How much does it cost to run one of these schools? And why aren't there schools on every train platform across India? It was there that I had my moment of obligation. And so I decided not to get the MD PhD. And instead, at the age of 24, founded the Global Fund for Children. The idea was to invest small philanthropic amounts of capital into innovative grassroots initiatives serving the most vulnerable children in the world. The philosophy was that by partnering with innovative community-based organizations, we could work together to help young people fulfill their potential. And during my time at the Global Fund for Children, we supported young people in Afghanistan, Uganda, Cambodia, Guatemala, and many more. I led the Global Fund for Children for 18 years, and I remain proud of all we accomplished. But by then, it was the right time to let go of the reins. While on sabbatical at Johns Hopkins, I was approached by the board of trustees at Society for Science to become its president and CEO. I laughed. I told them I hadn't done science since I was 22, and my last published paper was in brain research then. Since 1921, founded by E.W. Scripps and William Ritter, the Society for Science has been dedicated to expanding scientific literacy, access to STEM education, and scientific research. The Society for Science is also publisher of Science News, which I read as a child, and producer of the Science Talent Search, which I competed in as a high school senior. The more I thought about it, the more it felt right. So on the day I came a decade ago, it's been a decade, I wanted to focus on expanding and diversifying access to STEM because for far too long, those in the field doing research did not reflect what the world really looked like. We needed to make sure that opportunities like the ones I had were readily available to all young people. So to address this challenge, we used a three-pronged approach. First, we leveraged our high-caliber journalism we had through Science News and Science News Explorers and made sure that public schools across the country had access to this important resource. We're now in 6,000 high schools in this country with 20,000 STEM teachers using science news in their classrooms because science is changing so quickly and textbooks are so old. We also wanted to create a suite of STEM outreach and equity programs which make sure that every young person can become a scientist or engineer if that's what they want to be when they grow up. And so we want to support students and teachers, because teachers are what matter. And third, we celebrated and award young researchers through our world-class research competitions, the Regeneron Science Talent Search, the Regeneron International Science and Engineering Fair, and the Thermo Fisher Scientific Junior Innovators Challenge. In the last 10 years, the Society's accomplished a lot, but what I enjoy the most is meeting the innovators from our competitions who are already making such a huge impact. Take, for example, 17-year-old Justin Wong and Victoria Wu from Texas. Using ultrasonic waves, they were able to create a filtration system that removes microscopic plastic particles from water. Or 18-year-old Emily Ocaso from Virginia, who used an artificial intelligence model to document incidents of biases in news reporting. And then there's 12-year-old Shania Gill from California, who invented an early fire detection system that uses thermal imaging to prevent household fires. She not only won the top prize at the Thermo Fisher Scientific Junior Innovators Challenge, but was also recently honored as the Time Magazine Kid of the Year. These students are not only making a difference in their respective scientific fields, but improving their communities. And just FYI, we have 80,000 alumni of our competitions since 1942 who've broken new ground with discovery and innovation. You know, Steve Jobs once said, you can't connect the dots looking forward, but you can certainly connect the dots looking backwards. I admit my career path is a bit unorthodox. As a young person, I wanted to be a scientist. Instead, I became founder of an organization, the Global Fund for Children. I also write children's books. I have 30 of them, I believe, now. But today, I lead the Society for Science, a 103-year-old institution dedicated to expanding science literacy and working with young innovators tackling the world's most intractable problems, reaching hundreds of thousands of students each year. And for me, those dots fit perfectly. Thanks so much for listening to me this evening.
I'm hoping we could just have time for a few
Sure.
questions, hopefully. So what do you think are the top pressing challenges for science today?
I would say a couple of ones. I'm extremely worried about the misinformation and disinformation in science. And as I was speaking to young scientists today at Montana State University, when I spoke to them as young people and speaking to young people throughout the country who are budding scientists and innovators, they have a real responsibility to be excellent communicators. And I think every science major, whether in engineering or the natural sciences, needs to take a writing course and a communications course, and to be able to talk about their science in plain speak. I'd also say the second thing is climate science and climate change. That's really keeping me up at night, but keeping young people up at night. I mean, we are seeing this across the board in many of our project submissions now about all different ways of solving the climate crisis. And third, I would say artificial intelligence. I think it's one of the most extraordinary breakthroughs in history. But we also need to understand the ethical dilemmas around artificial intelligence and being responsible stewards of this technology.
So to end on a positive note. What gives you hope?
I've got the best job in the world. I wake up every morning and say, oh, this young person is doing this and this young person's doing this. But let me just say, being here for the last 24 hours and being at the museum this morning, to see the pictures of Ted Hoff and Leroy Hood, who competed in the Westinghouse Science Talent Search, or Charles Lynn, who is one of ours, is quite a joy. I mean, this is what we need to do, is to keep investing in young people and helping them take risks and telling them that the power of science and engineering to improve lives is really important. And that's what keeps me really excited about the future, is the talent. And I think we're going to be okay.
Thank you so much for what you're doing, and congratulations
Thank you
on
so
your
much.
award.
Thank you.